In the introduction, the first module, we are going to give some definitions to talk about the main benefits, the limitations of the technology, as well as some applications.
Let's move then to the introduction. I want to see these things with you: definition, bit of history, the main advantages, some limitations, and some applications. First of all, definitions. What is an adhesive? An adhesive is a polymeric material that can join two materials together. We are talking about a polymer in terms of strengths. It varies between 5 and maybe 60 MPa. We are talking about a structural adhesive, an adhesive that is used to make structures like cars, like planes, like trains, that kind of things. Less than 5 MPa. It's borderline. Some elastomers can still be considered structural adhesives, but less than that, then we are talking about sealants. Then the materials that you are going to join, you can call them substrates or adherents. It's basically the same. And then the interface that you have between the adhesive and the adherent, it's called interface. You also have the term interface, which is a kind of mixture between the adhesive and the substrate. An interface is a line, an interface is more a region around the interface. You can see the joint, which is the whole group of materials that we just mentioned, as a series of links. So you have the top link for the top adherent, top link or bottom link for the bottom adherent, the link adhesion between the bottom adherent and the adhesive, the same for the top adherent and the adhesive, and then you have the adhesive itself. A joint should never fail here. The weakest link should never fail, should never be this adhesion. It should fail ideally in the adherent. If it fails in the adhesive, we can live with that, or in the top adherent. Never due to a lack of adhesion. It's nice to introduce the subject by telling the legend of Daedalus and Icarus, because it helps to understand that this is a pluridisciplinary subject. You need to know about a lot of things. You need to know about mechanics, physics, chemistry, if you want to be successful in this technology. And what happened in this legend is that they misbehaved for some reason, and they had to flew over the ocean. And they built wings, and they used feathers. And to glue the feathers, they use beeswax. In mechanical terms, the device was really good, and they could fly. It worked very well. But after a while, the beeswax melted due to the influence of the sun and due to the water of the ocean, and then they eventually fell down. So that's to say that you might have a device that is mechanically sound, but if you don't choose the right adhesive and you don't take into account, for example, the effect of water or temperature, then you are in trouble. So it's much more than mechanics adhesive bonding. Fortunately, we have better examples in the past about the use of adhesive bonding. This is a plane used in the First World War, made of wood. At that time, there was still not duraluminum, high-strength aluminum, and there was still not synthetic adhesives like phenolics or like epoxies or things like that. So they had to use natural adhesives, and they use casein. Casein is a subproduct of milk. But it worked, and they already at that time realized that adhesive bonding is a very efficient method of joining that enables to have a lighter structure. The aeronautical industry is really the pioneer in the use of this joining technology. This joining technology allows to have stronger structures so that you can alleviate the weight. Later, another breakthrough by De Bruyn, a very famous English chemist, which could modify the first synthetic adhesives that was used, phenol, with a more ductile adhesive, because the first synthetic adhesives, they were extremely brittle, and mechanical engineers don't like to work with brittle materials. They like to work with materials that will yield, that will have some plasticity, some toughness, and he could combine two types of adhesives or two types of polymers, phenol resource and vinyl, to make an adhesive that is much tougher and that can be used with aluminum alloy. Again, this is a development that followed the Second World War. Unfortunately, every time there are wars, there are big developments in technological terms. But why adhesives can give a stronger joint? This is difficult to understand. It was for me, at least at the beginning, because I was told you have a material that is very weak, maybe 10, 20, 30 MPa, and that is used to bond a material like high-strength aluminum of 500 MPa, or that is used to bond high-strength steel, which is 1000 MPa, or who is used to bond composite materials that can be 1000 or 1500 MPa, but still they are used. Does it make sense? Not really. It makes sense, however, if you use properly the adhesive in the joint. You have here three examples. It's similar joints but different joining methods. You have welding here, you have rivets here, and you have adhesive bonding here. This is a joint that you can see typically in the fuselage of an aircraft. Let's look, for example, at the rivet. The rivet, you have here a side view when it's loaded, and it's loaded due to the pressurization of the plane. Every time there is a flight, the plane is pressurized, so this puts this kind of loading in the joints. Then if you look through the width, you will see that next to the holes of the rivets you have stress concentrations. So the average stress that the plate can take is limited by these peak stresses. On the other hand, if you look at the case of an adhesive joint, then you don't have any peak. If you look through the width of the joint, it's perfectly uniform. So you don't have these big peaks, and you use in a more efficient way the whole area that is being bonded. And this allows you to have, at the end, a higher strength, because you use a bigger area. You compensate the low strength of the adhesive with the bigger area and a more uniform stress distribution. That's really the secret. That's one of the most important slides of all the slides that I'm going to show you in this course. Because you have a better stress distribution, then this leads to a better fatigue strength, because fatigue is very linked to peak stresses that you have in the structure that might damage locally the structure and put it in plasticity and eventually crack it. If you don't have these peaks, then it's a better fatigue behavior, which is shown here in this graph, where you have the stress applied versus the number of cycles. And you have three curves. You have a curve here for the rivet, you have a curve in blue for the adhesive joint, and you have a green where you don't have any joint. Well, what this tells you is that an adhesive joint is nearly as good as the case where there is no joint at all. This is really a very impressive result. Also, because of the polymeric nature of the material, then you have better vibration damping. It dumps better the structure than if you use a bolt, for example. And this also contributes to have a better fatigue strength. More benefits. You can join dissimilar materials. This is also fantastic because you can join whatever you want. You can join, for example, ceramic with composite, composite with metal. There is absolutely no limit. Composite with plastic, plastic with metal, anything you want, there is no limit. This is not the same, for example, if you think about welding. You have much more limitations. Then it's able to join efficiently thin sheets. This is quite important. It's in benefits, but it could be also actually in limitations. We are not going to bond thick plates. We are always going to bond thin plates. What's the reason? If you use thick plates, I remind you that the strength of the adhesive is way lower than the strength of the plate. If you do something like that, of course it will break here at the butt joint. Well, okay, you can do an overlap and take advantage of a bigger area. But even like this, because the substrate is so thick, it will still break easily in the adhesive. Doesn't really make sense, this. What makes sense is this. Well, this again doesn't make sense because it will fail in the adhesive. But if you do this, if you do an overlap, then the area for the bonded joint is huge in relation to the resistant area of the substrate. The substrate is very strong, but small resistant area. The adhesive is very weak, but big resistant area. And then you can compensate like this. And you have even cases where the joint fails in the substrate, because if you multiply the strength of the adhesive by the resistant area, you are actually in a situation where you are stronger in the joint than in the substrate. So it makes sense only to use thin substrates. That's very important. It is the most convenient and cost-effective joining technique. Arguable, maybe the people from welding, they will not agree with me, but I strongly believe in this point as well. You have an increase in design flexibility. You can even invent new materials. And I'm talking here about the honeycomb structures, which are explained here in terms of behavior, in terms of stiffness, in terms of strength, and in here in terms of production. So basically you have the honeycomb, you have the skins that are very strong. The honeycomb, basically it's nothing, it's a foam or really a honeycomb, and between the two you use a film adhesive to bond the structure. You have one case here. The foam is very thin here, you see, and you have the skin. And I can bend it easily, can you see? No problem, very, very easy to bend. Now, if you increase the size of the foam, now you can clearly see that it's about the same size as the skin. In terms of weight, this and this is exactly the same, because the foam has nearly no weight. But if I try to bend, already a bit more difficult. If I increase more the thickness, it's getting more and more difficult to bend. This is related to the bending stiffness of the beam. And the higher the thickness of the beam, the higher the stiffness by a factor of 3. So really a huge impact. If you go for this, really a big increase, then I can't bend anymore. And I remind you, this is as light as this. Okay? In terms of light, you don't increase the weight of the structure. What you do is that you increase a lot the stiffness and the strength. If you want to see how much, it's written here. If you go from multiply by 2 the thickness, the stiffness increases by 7. If you increase by 3 the stiffness increases by 37. It's really very, very impressive. Okay, you also have smooth shapes when you use adhesive bonding. You don't have the marks of the bolts or the rivets or the welds. You have a continuum contact between the surface. This is good in terms of stress distribution, but also good in terms of resistance to corrosion, for example, and vibration damping. And in general, it reduces costs. Again, this one is arguable. But so far, it's all good. It's a wonderful word. But that means that there is no disadvantages, there are no limitations. No, there is. And maybe the most important one is this one that I'm going to describe you now. This is really extremely important, and it's the main limitation of this technology, which are the peeling loads. You should really be very careful with these loads and avoid them at all costs. And to make sure that you understand this and that you will remember this, I'm going to make a small demonstration. So I'm going to take a tape and I'm going to use or to disbond a bit of tape. Which loading am I applying to disbond easily a piece of tape? You can see that it comes off really, really easily. I am applying absolutely no effort at all. We are talking about a PSA adhesive, pressure sensitive adhesive. This is an adhesive that is always tacky, doesn't change the phase. It's always tacky, it's not liquid, it's not solid, it's tacky, okay? and it bonds when you apply pressure, okay? Well, easy peasy. The loading is peel, I'm applying peel, and all the load is concentrated in this line. The resistant area is aligned, so really very reduced the resistant area. That's why I am making no effort in peeling the tape. Now I'm going to do another joint. I'm going to use exactly the same substrates, this plastic, this adhesive, but I'm going to joint in the different way and load them in a different way so that you understand the impact of a good joint design. This is the worst joint design you can think of, which is when you apply peel. I'm going to apply another kind of loading. So I'm going to take two parts, two tapes. One part, okay, and I'm going to bond the other part on top of the previous part. But I'm not going to bond the PSA on the PSA. I'm not cheating. I'm bonding the part that has PSA with the part that has no PSA. Exactly the same conditions, okay? So you have the two substrates and you have one on top of each other. We are creating basically a single lap joint, okay? And we are talking about thin sheets, which is what I explained before with the red substrates. And now I'm going to load. If I load like this, the substrates are being loaded in tension, and the adhesive, the PSA, is being loaded in shear, okay? And the resistant area is huge for the PSA, which is the width times the overlap, okay? The overlap is quite big. It's this part here, and the width. The strength of the polymer is very reduced. It's the thickness of the plastic, which is very thin, times the width. So in terms of resistant area, it's really completely different. Now it's time to load. Okay, let's load. So I'm going to load. I'm loading. You can see that I'm doing a huge effort at the moment. I'm nearly fainting, actually. It's still strong. Still. And it finally fails. And it fails outside the joint. The joint is intact. So we have really a situation where we go from very low strength to high strength, where the weakest link actually is not the joint, it's the substrate itself. That's the ideal situation. Okay? When you have one of the substrates that is flexible, you have peel loading. When the two substrates are rigid, for example, here, when the two substrates are rigid and you try to wrap a peel, we are talking about cleavage. But it's basically the same type of loading. It's when you concentrate the load in a small area. Okay? Okay, so we understood this is by far the best solution because we load the adhesive in shear and we have a huge resistant area for the adhesive. All of this is resisting. The substrate is just this part, okay? The substrate is true, it's stronger, but the adhesive, it's weaker, but it has a huge resistant area. This one is exceptional. Sometimes you need to do that, but this only makes sense when the strength of the adhesive is similar to the strength of the substrate. Otherwise, of course, it will break in the adhesive. And also, if the loading is not perfectly aligned, then you can have cleavage. So this is to be avoided. This is number one joint by far, single lap joint, okay? But there are more limitations. We are talking about a polymer. Polymer, they don't like very much temperature, so if it's very high or very low, we are in trouble. You will see in the theory of adhesion, the adhesive is always applied in the liquid state, so you need fixing tools until the adhesive hardens. In general, you need to clean the surface. You know that. I'm sure you have done works at home with super glue. You need to prepare the surface. Some adhesives, they need temperature to harden. You need to put them in the oven or heat locally. Another limitation. Quality control. Some defects are really difficult to control or to detect non-destructively. One of them in particular, which is weak adhesion. The adhesive adheres, but not with the force, with the adequate force. And finally, there is no universal failure criterion. There is not one criterion that can design all the joints. You have many design criteria. So it's difficult to know which one is the best, and many times the engineer is a bit afraid, the engineer that does not know this technology, and he chooses another bonding technology. Some applications, we are talking about aeronautical, aerospace applications, of course, airplanes. You have here several examples, for example, fuselage panels, doublers and stringers, helicopters for the rotor blades, very common, rockets for the main body sections of the bonded honeycomb, but you have others you can see later. Thermal insulators for aerospace vehicles. You have here a very nice example, a vehicle or an aerospace vehicle that is protected with cork. Cork is a very good insulating material. It withstands very well temperature, but you need to bond it to the metallic structure. So you use adhesive. In general, it's a type of silicone adhesive that can withstand very well very high temperatures. And that's it for the introduction. You have an idea of the good things, the bad things, and some applications to open a bit the appetite and to motivate you for the rest.